Okay, so let's look at the how the impotency of the fracture mechanics is. Uh, so first, if we like to design a component or a machine parts, right? If we know the component design and apply stress, and we can develop a manufacturing method or process uh, such that the maximum flow size will be below the critical size, which is depend on your design, right? It's like we already mentioned previous class that the aircraft wing, right? What's the maximum flow size on the aircraft wing that you design, right? And which was highly dependence on the failure stress, okay, failure stress. Also from the Griffith's law, crack law, tells us the crack will concentrated at the crack tip, right, at the crack tip, okay, at the crack tip. And if our materials is brittle, such as ceramics, alumina, or glass, if there's a crack inside or on its surface, if its crack size is long and its a radius crack radius is small, that means it's a highly concentrated stress will be located at its crack tip, and its actual stress on the crack tip is about 2 times applied stress square root of the ratio of the crack size by the crack radius, the tip radius. Okay, the tip radius. Okay, so we can realize that the real structure located at the crack tip is about this. Okay, depends on the Griffith's crack law. Okay, let's look at the ductile fracture. Okay, it normally occurs in a triangular fashion and creates dimples on the fracture surface. Okay, so when a ductile materials withstand a tensile stress, when the stress is higher than the UTS, ultimate tensile stress. So what's the mechanical phenomena will occur? Necking, right? The necking occurs as the applied stress reaches the ultimate tensile stress, right? And from the materials point of view, that some voids form inside the materials, right? Inside the materials, the micro voids, okay? And when you keep pulling it, okay, when you keep pulling this ductile materials, the micro voids will form and create numerously, okay? And finally, the collisions of the micro void will form. Right? That means those micro voids connected, okay, connected. And finally, it will fracture the sample. It will fracture the sample, okay. And this micro void formed due to the sleep process, due to shear stress, okay, to trigger the sleep process that already mentioned previous chapters. Okay, therefore, if we just focus on the fracture surface, of the ductile materials, we observe numerous of the oval dimples. Okay, oval dimples and round uniaxial dimples. No, along this fracture surface. Therefore, we can tell whether it's ductile or brittle fracture by observing its fracture surface. Okay, so for the brittle fracture, involves it involves a little or no plastic formation. Okay, that means its failure could be a catastrophic disaster. That means this failure occurs immediately without any warning because there's no plastic deformation. Okay, and the brittle fracture occurs along the specific crystallographic plane. So what's this plane that we already mentioned previously in previous chapters? What's this? Well, what's this specific crystallographic plane? Do you guys still remember that? It's the closed pack plane, right? Mostly you will follow your fracture will slip or your fracture will fail along this closed pack plan. Okay, mostly. Okay, and can be identified by the fracture surface pattern. As already mentioned, it's similar to that of the ductile materials, right? We can observe its fracture surface to tell whether it's brittle or ductile failures. Okay, and then for brittle fractures, its fracture surface will look like the rock candy or the chaffer's surface, candy or chaffer surface structure. Okay, and also you can observe this SEM scanning electron microscope image of for A it is alumina. For B it's what? It's glass. It's glass. Okay, so for both of this are brittle, right? Brittle materials. Okay, so what's the fracture behavior of polymer? We already discussed about this fracture behavior of brittle and ductile materials. And what about the fracture behavior of polymers? That means plastics. Well, polymers can undergo both ductile and brittle fractures. Well, it's quite interesting. It's quite interesting. The ductile and brittle fractures are coexistent. Well, it depends on the temperature or depends on the polymer's properties. Okay, so what's the category of polymers or plastics? How many types? First is thermoset. Okay, thermoset. One type of the polymer is thermoset. Okay, so what is thermoset? Thermoset. Thermoset undergoes brittle fracture. Let's say, okay, this polymer is thermoset plastic. It will undergo fracture, brittle fracture. Okay, below its class transition temperature, we always say it's Tg. It's a very important materials property. Okay, and thermoplastic fail in a brittle manner. Okay, so what's the three types of the polymer? First is thermoset or thermostable. The second one is what? Thermoplastic. The third one is elastoma. Okay, and for the thermoset, its fracture behavior is brittle. Okay, is brittle. So the thermoplastic, its fracture behavior is, it depends. It depends on Tg. It depends on the glass transition temperature. Okay, and some polymers fail in a ductile manner above the glass transition temperature. Okay, so what's the difference between thermosets and thermoplastic? Let's forget about the elastomer first. Let's just think of the first two types of plastics or polymers. So what is the definition of what's the physical behavior of the thermoset's polymer? What's that? Okay, so for the thermoset polymer, when we heat it up, I mean when we increase the temperature, the polymer, the phase of the polymer will transfer from the liquid phase to solid phase. Okay, to a solid phase. That means the thermoset, right? And when this temperature decrease to, say, the room temperature, and this thermoset polymer still remain. I mean, this solid polymer still remain. It's not reversible. That means when the temperature cool down to the room temperature and solid polymer still remain, it will not return to a liquid polymer. Okay. However, for the plastic polymer or the plastic polymer, that means when we increase the temperature that higher than TG, glass transition temperature, this polymer will start to phase change, right? Start to phase change from solid converted to liquid, Okay, and when the temperature is decreased to, say, the room temperature, this thermoplastic polymer will return to a solid. Okay. Okay. So I will just mention it again. So when this thermoplastic polymer converted its phase from solid to liquid with increasing temperature, and when this temperature decreased to room temperature, and this thermoplastic polymer will change its phase from liquid to solid. Therefore, we can realize that this TG is a very important materials property. Right? It can control the fracture behavior of a polymer. Okay, I will show you the picture in next slide. Okay, and fracture in composite is more complex. Generally, the fibers undergo brittle, while the matrix undergo the ductile. Right, the glass fiber is brittle materials, and the epoxy matrix is ductile materials. Okay, so it's quite complicated. Therefore, the bonding between the fibers or the fillers and the matrix, oh, is important. Okay, it's important. I will just mention this later. Okay, so look at this curve of the modulus, Young's modulus versus temperature. And this is only for thermoplastic. Okay, thermoplastic polymer. Okay, thermoplastic polymer. Let's say at room temperature, in the very beginning, this polymer, thermoplastic polymer, is glassy state. That means it's a solid, it's hard. Of course, its hardness is much smaller than metal and ceramics, right? And when we keep increase the temperature in this direction, its Young's modulus will keep decreasing. Will keep decreasing. At a certain point, the modulus will drop substantially. Okay, will drop substantially. Okay, and then this stiffness will reach a stable. Okay, with the increasing temperature. Okay, and we get the point and somewhere between between the glassy state and the rubbery state. Okay, between it, you get a midpoint between the glassy state and the rubbery state. We saw it's TG, glass transition temperature. So why is temperature so important? Why this materials property is so important? For example, we are gonna use the 3D printing to fabricate a plastic tool. For example, so the nozzle of 3D printer, whose temperature must be higher than TG. Okay, you may use the ABS or PLA and so on, right, for your 3D printing materials, right? And the nozzle temperature must be higher than TG. Okay, much higher than TG in this direction. Why? Because we need a float materials, right? We need a flow materials to draw or to build up my pattern. Okay, to build up a layer pattern, right? If the nozzle temperature is lower than glass transition temperature, lower than TG, maybe your nozzle will be clogged. Okay, will be blocked. Okay, so we have to keep this materials. It can be flow. We have to keep its viscosity to make sure it can to draw or to pattern what the shape that we designed. Okay, so we have to realize that how this TG is quite important. Okay, how this TG is quite important. Okay, let's look at the fracture behavior in composite. Okay, so as I already mentioned before, that the composite is consisted of the fiber, the glass fiber, carbon fiber, like fillers, and the matrix. Okay, and the matrix. And the most important factor for the composite failure is the bonding between the fiber and the matrix. Okay, the fiber and the matrix, the bonding between the matrix and the fiber. Okay, if the bonding is weak, and when this composite withstand a tensile stress or what different kind of stresses on it, so it will delaminate between the fiber and the matrix, and some void will form between them. Okay, therefore the fracture, or we say the strength will dramatically reduced due to this weak bonding between fiber and matrix. Okay, and also the other failure mode for a composite is the layer. Okay, the layer. If the individual layers of the matrix are poorly bonded, the matrix might delaminate, creating void. Okay, so in the figure A, the case is the weak bonding between fiber and matrix, right? And the second, the failure mode of composite is weak bonding between layers. The first layer and second layer and third layer, right? Even though the bonding between the matrix and the fiber is strong, if the bonding between layers weak, well, the fracture or the crack will form between layers like this. Okay, this is the crack. Okay, the crack will form between layers. Okay. Okay, so let's look at the other behavior is called the creep. Okay, so what's the definition of creep? That is the time-dependent permanent deformation of the materials under constant load or stress at elevated temperature. Okay, and materials can be considered fail by creep even if it hasn't fractured. Okay, and stress ruptures is the fracture induced by creep. Okay, so I will introduce this creep phenomenon later. Okay, and the second we have to concern is that the stress corrosion. That is the phenomena in which the materials react with corrosive chemistry in the environment. Well, if this corrosion occurs, these components or parts might fail, even the applied stress is below the yield stress. Okay, and it can be identified by examining the microstructure of the fracture surface. Okay, so let's focus on the creep behavior. So when these materials is withstand a tensile stress at an elevated temperature, and this stress is constant, that means we do the tensile test at elevated temperature T, and this stress is remain a constant. Therefore, you can think of this way. Okay, if this sample, this raw-like sample, withstand a tensile test at room temperature or ambient environment, and this applied stress is below its yield stress, what's going to happen? Right? Nothing will happen. That means when this stress is released, this sample, the length of the sample will return to its original length, right? Therefore, nothing will change. Okay. Okay. And if the tensile test is under an elevated temperature, even we apply a stress which is lower below the yield stress. Okay, and this deformation will be permanent. Okay, so you can compare the difference with the room temperature or ambient environment and elevated temperature. Okay, therefore we can measure the sample's creep behavior by applying tensile test at an elevated temperature. Okay, and we can measure its strength versus time. We will get a curve like this. Therefore, you can look at there are three sections of this creep behavior. Okay, the primary creep and secondary creep. Okay, and tertiary creep. Okay, so in the primary creep, the slope, aside the creep rate, I will discuss this later. Usually the creep rate is always be indicated at the secondary creep, but not the first and third. Okay. Okay, so let's look at the creep rate. The slope decreases with time, right? That means the slope at the primary creep, okay? The slope, right? Keep reducing, right? Therefore, the slope decreases with time. Then for the secondary creep, it's a steady state. That's a steady state. What's that mean? That's the constant slope. Okay, therefore, that's a linear relation. It's a linear. And the slope is constant. Okay, the slope is constant. So we always define the creep rate is the slope within this secondary creep region. Okay, and finally for the third creep, that the slope decreases with time. Oh, sorry, increases with time. Okay, and the slope increases with time, right? Increases with time. So what's that mean? That's mean the acceleration of the creep rate. So its failure will be facilitated at the third stage. Okay, at the third stage. Okay. Therefore, in a Crip test, a constant stress is applied to elastical firm heat displacement. Okay. Therefore, in the very beginning, there's an elastic strain, right? Elastic strain, and you will undergo the first stage and the second stage. The second stage is the steady state, and the third stage, that's mean the slope increase with time, right? The slope increases with time. Finally, the sample will rupture. Okay, will rupture. Therefore, this test, the Crip test, this Crip test will be at the constant stress and the constant temperature. Okay. So let's evaluate the Crip behavior. Okay, dislocation clamp is enabled by high temperature. The dislocations move or diffuse in a manner that causes the formation of the sample even at low applied stress. Okay, so why this dislocation is clamped? Okay, why? Okay, yes, let's think of this way. At the elevated temperature, these elevated temperatures will increase the ductility of the materials, right? That's mean this materials is easy to deform under a low stress, applied stress, right? Under low applied stress. Therefore, if we keep defaulted or keep applied stress, that's mean the sleep process keep occurring inside this sample. Okay, and this sleep processing will cause this dislocation clamp. Okay, will cause the dislocation clamp. Okay, and the creep rate is the slope of the steady state portion of the stress strain curve of a Crip test. Okay, therefore you have to remember that the creep rate is only for the steady state portion. That's mean the secondary creep. Okay, secondary creep. Secondary creep. And the rupture time is the time required to failure to occur in a Crip test. That's mean this point. Okay, that's mean this point. Okay, it's the rupture time right here. Okay, and it's the creep rate right here. Creep rate right here. Okay. Okay, so let's look at this figure. It shows the relations between creep rate, rupture time, and which accounts for the combined effects of stress and temperature. Okay, for example, in this figure 1, 1, 2, and 3. The 3 curves in this figure. Okay, so can you tell me if we fix the temperature? Okay, we fix the temperature. Okay, say it is a constant. The temperature is a constant. And we apply the different stresses. We apply different stresses. We got this figure with 3 curves. Okay, we got a same temperature, and we got a different stresses. So can you tell which curve? I mean, the curves represent materials, and this materials is high hardness or high strength or low strength. So can you arrange the strength from the highest to the lowest? If they are under a Crip test at a constant temperature, constant elevated temperature. So can you tell? Can you tell? Okay, so for the curve one, it has the higher stress applied, right? It has a higher stress applied, and its strength is what? Its slope, let's say the creep rate. Its creep rate is higher than that of the second one, and it's higher than the third one. So what's the definition of the creep rate if it is higher? If the creep rate is higher, so what's its definition? Let's look at this one. The slope, right? The slope. If the slope is higher, that means the deformation rate is higher, right? The deformation. That means within a short time, it's got a higher strength. Okay, it got a higher strength within a short time. Within a short time. Okay, within a short time. Okay. Okay, so in other words, if this figure is tested under a fixed stress, say fixed stress, and with different temperature, So can you explain this figure? So which one is harder, or which one is stronger? Which one is stronger? We fix the applied stress and just change the temperature. Change the temperature. Which one has the higher strength? Yeah, you have to tell what's the differences between these three curves. Think of it. If I have the constant stress, of course, for the third curve, this one, its creep rate is the smallest one at a constant applied stress, right? Right. That's mean it's not easy to deform. It's not easy to deform. Okay. Therefore, we can estimate or we can predict that the sample from the third curve has the higher strength than others. Okay, higher strength than others. Okay, because its deformation is lower. Okay, so usually the temperature, the elevated temperature occurs at the temperatures are higher than 0.4 of melting temperature. Okay, so what's the curve when the elevated temperature is smaller than 0.4 melting point? It probably would be like this. Okay, probably like this. That means the strength remain the same. The strength remain the same. Okay. Okay, so let's look at the strain rate. It is a constant at a given temperature or stress. Okay, and the strain hardening is balanced by recovery. So we can look at this this formula that we are quite familiar with. It's a Arrhenius equation, right? It's a exponential function. It's a exponential form. Okay, it's a Arrhenius equation. So we can define this strain rate. Strain rate equals to constant times the applied stress with a stress exponent n and exponential of minus activation energy for creep divided by constant R and the temperature T. Okay, the same, we can convert this exponential function to log, right? Log graph. We will convert it to a linear relation. Okay, we will convert it to a linear relation. Okay. Okay, so we can look at the figure shows here. The strain rate increases with increased temperature and the applied stress. Okay, so if we have a materials that it shows in the applies there's a materials that the is test at elevated temperature for 427 Celsius. Okay, a Crip test, a Crip test. So when the stress increase from here to here, right, and its strain rate increase, right, its strain rate increase, the steady state creep rate, the steady state creep rate. So the x-axis represents what? The slope. The slope present here. Present this slope. Okay, the slope. Okay. Of course, the higher temperature will cause the fast or slow rate. Okay, so we can compare with, for example, like this. For the 438 Celsius, if we have a higher stress, right, we get a higher strain rate. Okay, we get a higher strain rate. And if we get a higher temperature, we get a higher temperature. So let's plot this figure like this. Like this. Right? Like this line. Okay, and this point has the higher temperature, 538 Celsius, and this point has the lower temperature, 427, right? So for the temperature at the 538, got the higher strain rate, and when the lower temperature, right, its strain rate is still lower. Okay. And by Crip testing, we can develop stress rupture curves that estimate the expected lifetime of the component for a given combination of stress and temperature. Okay, so look at this figure. Can you arrange or can you develop an experiment to plot this figure? Right, you can think of how to plot this figure. How to plot this figure combining the parameter of the stress and rupture, rupture time, rupture life. Okay, so what this figure tells us? What the figure tells us? So if you have a constant applied stress at different elevated temperature, what we get that for the lower temperature is 980 and 1040, 1090, right? And we get a longer rupture time, right? We got a longer rupture time, right? And if we can design it, okay, that's why we design its rupture time right here. So what's this figure tell us? That's mean you can realize that this component, if we already design its rupture time under a Crip test, therefore we can estimate, oh, what's the applied stress? Could be at the different elevated temperature. Okay, so for example, if we wanted the rupture time right here, and if this material is test at this 460, we got its applied stress, right? And if this material is tested at 870, and we get its stress. You can see the stress is getting smaller and smaller with what? With increased temperature. Okay, therefore, if this material is heat treat is at the 460 Celsius, and we already design its rupture time. Therefore, you know the applied stress for this component or for this mechanical part cannot be beyond this applied stress. Okay. And a guy is called Lawson-Miller who developed an index called the Lawson-Miller parameters, LM, that solidates the stress, temperature, and rupture time. Okay, the three parameters: stress, temperature, and rupture time relation for the materials into a single curve. Okay, so we have so many curves right here in the previous slide, and we can combine those parameters, stress, temperature, and rupture time into a single curve. Okay, and this guy is called the Lawson-Miller. Okay, Lawson-Miller. By the experiment. Okay, therefore we have this index is called Ln value. This Ln value equals to time the temperature divided by 1,000 times the coefficient A and B log T time. Okay, this is the temperature and this is the time. It's time. Okay, and we can get a linear relation. Okay, in this case, right, it's a linear relation. Okay, we got a Lm value as the x-axis. Okay, and the stress, applied stress. Okay, applied stress for y-axis. Okay, and AB can be, it depends on the materials. Okay, A and B are depend on materials, different type of materials. Okay, so yeah, so AB are materials dependent. So this course will be ended here. So we'll see you next time.